and what approach you should have followed and what you should have done, that all will be discussed in the lab session. Okay, so let us start today's lecture. So today is 11th lecture for advanced electric drives, and we are basically now discussing the basics of induction motor. So we have seen how the flux is generated, and then how we can realize the rotating flux vector using a space distributed three-phase balanced power supply. So this is what we are having. So we have distributed the windings, and so what we see in effect, that if R, Y and B are balanced in time, that means IR plus IY plus IB equal to 0, then we have a smoothly rotating counterclockwise direction rotating flux. So which is responsible for the rotation of the motor due to principle of induction, electromagnetic induction. So this all we know. Now we have moved towards the equivalent circuit. So this is the typical equivalent circuit what we have seen earlier as well. So little bit more understanding we are trying to gain about this equivalent circuit and the phasor diagram, which will be useful in lot of computations, particularly related to assessing the performance of the motor and let's say drive we are talking about. So first we have seen that how the torque speed characteristic can be visualized in a simpler manner. So we have tried to come up with some expression for the rotor current, and then we have got the electromagnetic torque, and it is coming out to be a simple expression which is something like this. So where alpha is basically the ratio of RR and XLR, rotor resistance and rotor leakage reactance. So two extremes we have discussed, that when S is very less than alpha by 2 and S is very greater than alpha by 2. So we have simpler forms of this characteristic. So one is a straight line, another is simple hyperbola. So one mistake what actually I made while drawing this, that these characteristics are meeting at kt by 2 at alpha by 2 x-axis, and the value is kt by 2, but the value of actual torque is not kt by 2, the maximum torque. So if you plug in alpha by 2 in the expression for this torque here, so this will turn out to be kt by 4. So this correction is there from the previous lecture. So the resultant characteristic what will be there will not be exactly following the line or exactly following this curve, but it will deviate from this at some point over here. Let us say half of this, whatever I have drawn actual. So this point is kt by 4, and the characteristic will deviate here, and then it will merge with the approximate characteristic after some point. So this blue, or maybe I'll draw with black, let us say, for little bit clarity. So, but these points are correct, that the maximum torque occurring at alpha by 2 and all these things are correct. So little bit smooth characteristic will be generated, and it will follow. Even the values what we have seen at s equal to 1, this is also correct. So there is no problem in that. And similarly for the generation mode also, we will have kt by 4 as the value, and this is little bit smoother and then following this. So the nature is more or less like a straight line during this zone, and it is something like 1 by s in this zone. And in between it is just meeting these two characteristics somewhere. So this is clear, right? This was the correction what we have from the previous class, and rest all things are fine. The maximum value of torque what we are getting at this alpha by 2 slip is basically something like kt by 4, where kt we know that it is some 3 vs square divided by okay, some p by 2 is also here, so omega s and xlr. Correct? This is what is the constant what we are having. So with this we can compute, because all these things are constant, so we can easily compute what is the value of torque. So if you know this constant, you can compute the value of torque at any point in this characteristic just by varying the slip. So this portion of the expression will change, the rest all things will remain constant. Clear, right? Is that clear to all of you?
Yes, sir.
Yes, sir.
So this was the correction, and then other things, whatever we have seen, we are able to derive the point where it should occur, the maximum value. And we have seen that even with the exact Thevenin's equivalent and all, it is coming close. It's not very far from whatever other ways of derivation are there. Okay, now we are going towards the rotor resistance insertion. Okay, some of the things are deleted. I don't know why. Okay, I will draw it again. So we have seen the effect of inserting some resistance within the rotor circuit. So particularly for wound rotor motor, we are finding this useful. So if we want to improve the starting torque, little bit more detail we will see today regarding that and other starting, whatever ways we use to start the induction motor. So first, let us say when we have the induction motor and we try to attempt direct online start, what are the problems? So first we should understand why it is problematic, what are the real damages that may occur in the motor, and then we can go ahead to make it little bit better, whatever better we can. So say again, we take the approximate characteristic, approximate equivalent circuit what we have. And we will see where it deviates from the actual also, little bit more discussion on that point. So this is what it is there as of now. Now the quantity, the rotor current what is there is more or less the stator current. That's what we know because this magnetizing current is only a small percentage, so we can ignore. So more or less the rotor current is what we have as supply current. So if we compute rotor current, which is almost equivalent to computing the actual current going into the motor. So we will take this approximation and compute this. Which we have done for the torque computation as well. So this is the expression what we have got. And here actually particularly we are looking for case where slip is 1. The previous case was any general slip, but here we are talking about the starting the induction motor. That means slip is equal to 1, or in other words the rotor speed is equal to 0. And we have given the supply at rated voltage and rated frequency to the motor. Now what will happen to this rotor current, or what will be the value of the rotor current, that we should see quickly. So we have S goes to 1, so this becomes RS plus RR, and this is as it is. Now for most of the motors we have discussed that XLS and XLR are almost equal, the leakage reactances are almost equal. Even many a times the stator and rotor resistance are also very close. So this approximation can be taken and this can be written like RR square plus XLR square. Something like this. Okay, again, if we have the XLR coming out of this square root and we equate this alpha as RR by XLR. So this is a very important term actually. In all the derivations this will occur, or this will repeat itself again and again. So be little bit watchful wherever it is coming. And the value we know that it is something close to 0.2. So then we can have a very good estimate about what current we are going to see. So then we have Vs divided by 2 XLR, and in the square root we will have 1 plus alpha square. Now alpha, because this is 0.2, so alpha square will be something like 0.04, and so adding to 1 and then taking a square root will actually keep very close to 1. So that's why this term will be approximated to 1 and the remaining terms will be this. Now for any typical induction motor, we know that any of the leakage inductances are something like 10% of the motor rating. So 0.1 per unit is the typical value for the leakage reactances. This is in general true for many of the induction motors. So what we have basically that IR turning out to be Vs by 0.2 times of the, oh, if you say that, okay, let us take the per unit value of this directly. So what we will have that IR divided by the R base, and which is basically Vs divided by V base, and 2 times of XLR divided by X base. Fine. So this is basically we are feeding 1 per unit voltage over here. So this numerator is 1. And this we have seen that something like 0.1 per unit. So this becomes 0.1. So this turning out to be 5 per unit. Fine. So the rotor current what we are seeing is that when we do direct online start, this is the magnitude of current we may have going into the motor. So yes, we know that the starting current is very high, but we should also be able to quantify that when we are saying high, what is the meaning of high? How good it is or how big it is? Whether it is 10 times, 20 times or 3 times or 1, no, just equal to the rated value. So this is a good estimate of what we are going to see in the system. And when I say per unit, this is true for any power rating. You can simply scale it with the base current or the rated current. So you can see how it will be. Now, if we talk about another factor which is very, very important, the power factor of the this power whatever is flowing in the induction motor, this will basically total resistance, total reactance. So when I say total resistance, this is basically again from the equivalent circuit RS plus RR, and total reactance again from the equivalent circuit XLS plus XLR. So the power factor will turn out to be something like this. So being an engineer, you must know that what you are dealing with when you are going to start any motor direct online. You should have good estimate of what current it may take during the starting. So then if we simplify again similar to what we have done earlier, so it will come out to be XLR, and again because RS and RR are almost equal, we have said, so this becomes 2RR by XLR, and again this will come out to be 1 plus alpha square. Fine, no problem in this simplification. So what we have now here is that power factor is coming out to be RR by XLR approximately, and which is our alpha value, which is 0.2 more or less. So we see that power factor is very, very poor, though it's not 0. Correct? Fine, right?
Yes, sir.
And this is the power factor which we are going to observe when we have this something called as the blocked rotor test. Because conditions are same. Blocked rotor also we have is equal to 1, and we are giving voltage at rated frequency. So when we have rated frequency, the values of reactances are rated. So then this power factor we are going to observe during the direct online start as well as during the blocked rotor test. Now, this is the power factor, and then what is the power absorbed by the motor? So this is certainly 3 Vs Is cos phi. And for uniformity, let us take the per unit value of this also. So P divided by P base, which is basically 3. So here also 3 will come, Vs by V base, Is by I base, and cos phi. So which is basically V per unit, I per unit, and cos phi. This is what is the amount of power you are going to draw in the motor when you try direct online start. So the number would come out to be, voltage is given as 1 per unit, the current you have seen it is 5 per unit, and power factor is something like 0.2. So turning out to be more or less 1 per unit power you are absorbing in the motor. Looks pretty okay. But if you think that, say you have a 10 kilowatt motor and you are doing direct online start, this complete power is flowing into the motor. And what is the mechanical output? What is the mechanical output at starting?
0.
0, because speed is 0. So what is happening? This total power, whatever you are taking, is basically getting burnt in the motor resistances. So which means 10 kilowatt you are burning inside this motor, and which is not a small power if you see from the thermal point of view. This will heat up the motor very quickly. You understand the point? So 1 per unit power going inside the motor is not good if you don't have any mechanical output. Yes, I'll come, sir. So this is the thing, right? Now, what happens to the torque? This is another important factor. We must know that what is happening with our torque. This is the general expression. Here we have to insert S equal to 1. So tau starting is basically kT times of alpha by 4 plus alpha square, which roughly you can say is kT by 4. Understanding my point? Okay, alpha is also there, sorry. Correct? And we know that our maximum starting torque is basically kT by 4. So this is roughly equal to tau max times of alpha. So the ratio of starting torque and maximum torque at the direct online start is nothing but alpha. Understanding my point?
Yes.
So this is what we are going to get. So 4 parameters what we must see when we are dealing with a motor and any method of starting we are doing. So first one, we must know what is the current flowing into the system, into the motor. Second one, we must know what is the power factor that we are going to see for the current. And then third is the power. What is the amount of power that motor is going to absorb during the starting? And then the torque. If these 4 parameters you can quantify, that is all. This is enough for motor to tell that how your system is going to perform during any starting. Fine, right? So obviously this is poor. Alpha is only what? 0.2. So 20% of the starting torque you are going to get when you do direct online. 20% of the maximum torque. And for that you are pumping some 5 times of current and burning almost the rated power in the motor. So which is very, very bad for the system at all. Overall the system is going to suffer. So what we do, we improve these numbers by doing some arrangement. So one arrangement what we have seen in the last class, that if we insert some rotor resistance, let's say we are talking about wound rotor motor. So if we insert some resistance in the rotor circuit, we may see some improvement in the starting torque. The other things we have not discussed. We have only seen that the starting torque may improve. So we will take that point and see how the other parameters are behaving when you have rotor resistance inserted in the circuit. So obviously the equivalent circuit we keep like this approximate one. So say this R external is our resistance inserted in the circuit, and this is our rotor resistance. Then we have XLR, XLS and RS. Again, because we know that when we are talking about the characteristics over here, we are trying to achieve maximum torque. Correct? So maximum torque is achieved when slip goes to 1. The X max slip goes to 1. Which means this should be maintained. So always this maximum torque is occurring at alpha by 2. So then what we have basically is that alpha turning out to be 2. And we have seen that for this condition, we will have R external given as 2XLR minus RR. So for this condition, we will see that how our circuit quantities are going to behave. Correct? Okay, so first our rotor current, how it's going to be. So what we have basically IR Vs divided by this total resistance. So total resistance meaning Rs plus Rr plus R external plus XLS plus XLR whole square. Now again we can take out XLR from this, or maybe we can do some approximation here. So now if you see Rs plus Rr plus R external, this is nothing but, if you first write the actual value, R external is 2XLS or 2XLR minus RR. So basically this is coming out to be Rs plus 2XLR. Understanding my point? Again, this reactance value may be a little bit higher compared to resistance. That's the general trend. So we can simplify this or approximate this to only twice of XLR. So what we have here, when you plug in these values and including the previous assumptions that XLS equal to XLR, this will come out to be this. Fine. This is correct, right? So now, yes. Yes, any questions? Okay. So what we have then, that IR, when we have this rated value of voltage, so and XLR is something like 0.1 per unit. So in per unit, this value will turn out to be or nearly, you can say something like 3.5 per unit. So we are able to cut down the current somewhat. Now it is not going up to 5 per unit, but it is restricted up to 3.5 per unit, 350% of the rated motor current. Correct? Now, definitely our current has reduced. Now what has happened to power factor? It should improve. That's the general understanding, because we are inserting resistance in the circuit. So we have R total divided by Z total. So R total is basically again Rs plus Rr plus R external, and this divided by the whole value Rs plus Rr plus R external square plus XLS plus XLR square. This term, whatever is in the denominator, we have seen this is approximately 2 XLR times of root 2. Okay, this is what we have, right? This approximate value for this is something like 2 XLR. This is also 2 XLR if you take out 2 XLR root 2, and this is also 2 XLR. So then this turned out to be 1 by root 2, which is much better. The power factor, which was something like 0.2, now it has improved to 0.707 after inserting this resistance. So that is a good improvement in the power factor. Okay, now what is happening to power? The next parameter. Again, we directly take the per unit value. So we have Vs per unit, Is per unit times of cos phi. So 1 per unit we are injecting the voltage. Current is coming out to be 3.5 and the power factor is 0.707. So how much this will be? Any quick computation? So now onwards, no, you start sitting with your calculators as well in the class. Okay, compute. How much is the value?
2.47.
Yes, approximately 2.5 per unit. So what we observe over here that actually our power intake has increased. Understanding my point? We have improved on the torque that has gone to the maximum value. But our power intake, because still our PM is equal to 0. So all this power is coming into the motor. But are you burning this whole power in the motor or is it getting burned somewhere else as well? So there are two components. One, what is going to the factor RS plus RR. That means the power lost in this. And the other factor is IR square times of R external. Understanding my point? The total power is basically divided like this. It is not like 2.5 per unit is entirely going into the motor. There is external resistance also connected over there. So what percentage is going in the resistor, what percentage is going in the motor? Because ultimately we are worried about this, the component which is going inside the motor. So we can quickly compute this value. We know that RS plus RR divided by R external. This will be the ratio of power which is flowing in the motor and in the external resistor. Okay, maybe I should not write PM because M was for mechanical. So PS I can say. So if you again compute this, so we know that this R external will turn out to be 2 times of XLR approximately. This is, let's say, 2 times of RR. So this is nothing but our ratio alpha again, which is 0.2, which means whatever power we are burning in total, the 20% of that is going for the motor, which means 0.2 into 2.5. So how much this will be? 0.5 per unit. This is what is basically going in our motor as loss. Rest of the 2 per unit is basically going in the R external, is getting burned over there. So it is all right. We have cut down the power which was getting burned in the motor as well. Correct? You understand the point here?
Yes, sir.
Yes, sir.
So although we have the power intake as 2.5 per unit, but this entire 2.5 per unit is not getting exhausted in the motor. A significant portion of this, 80% of this power is basically exhausted in the this resistance what you have added in the rotor circuit. So that way motor is little bit safe now. Instead of 1 per unit power which was earlier, now it is only 0.5 per unit power which is getting exhausted in the motor. Fine.
Yes,
so
sir.
quick comparison if you make between the direct online and the rotor insertion, this resistance insertion method, quick comparison if you make. In the direct online we had only 20% of the maximum torque. Here we have tau max. Here we had 5 per unit of current. Here we are having only 3.5 per unit of current. The total power taken is definitely 2.5, but the power going into the motor, like which is getting exhausted in the motor, is only 0.5 per unit compared to what was there 1 per unit for the direct. Okay, I am writing it opposite, is it? No, this is fine. Only power I have written inverse. Okay. So which was per unit 1 per unit here is basically 0.25 per unit here. Whereas the total power is 2.5 per unit. Power factor, what was 0.2, now has improved to, okay, there is no per unit in this, now has increased to 0.707. And that's all right, 1, 2, 3, 4. These 4 parameters we are able to see that there is improvement at every front. So that's why we say that yes, the rotor resistance insertion is a better method to start any motor compared to direct online. If your motor power is little bit significant, let's say even 5 kilowatt, this is also a big power if you want to start direct online. Okay, if here the current is something like 7 ampere, for direct online you may see like some 35 ampere flowing into the system, which could be a significant thing, and 5 kilowatt power burning in the motor with only 0.2 times of maximum torque available for your load to respond. So what may happen if you have lower starting torque? If your torque is lower, let us say omega is there, and say this much torque is available. So, or okay, let us draw omega with respect to time. So if the starting torque is small, the omega may take a lot of time to respond. And this amount of time what you are spending during the high slip operation, this could be disastrous for the motor. This zone where omega is small, this is basically high slip, and I'm talking about omega m. So if you have high inertia system, you should not go for direct online start because of obvious reasons. High inertia system may respond slow, and then when you have the starting torque something like 25 or 20% of the maximum torque, then still the response could be poorer, and the chances of getting the motor burnt may be very, very high. Understanding my point? Clear, right?
Yes, sir.
Good. Yes, sir. Now see the similar analysis we can do for other method of starting. What is other method of starting? We have the reduced input supply. This is another way of starting. For small motors, generally we see, for example, if our fan you see, the regulator is basically applying some smaller voltage. So for motors like that which are small in power, so this could be a good way to start. But for large motors, what will be the impact of that? This we can analyze through the similar analysis what we have done earlier. So again, 4 parameters. What is the rotor current? Say you are applying Vs as some 0.5 per unit of the rated. Then what is IR? What is the power factor? What is the torque? What is the power? These things we can compute quickly. And we can know whether our starting method is suitable for our motor or not. You understand my point? Now, if I just compare these methods, these two methods of starting in terms of the torque speed characteristic, what basically we are having is that this is the maximum torque, let us say, and this is slip equal to 1 and this is 0. So basically what we are trying to do, that if our characteristic is something like this, the actual characteristic in rotor resistance insertion method, what we are doing, that basically we are shifting this point where the maximum torque occurs towards the high slip region, towards S equal to 1, and the best can be achieved at this point. Correct? Now any resistance value in between will give better starting torque than what motor originally had. If you try to insert anything more than this value what we have computed, it will be useless because your starting torque will further reduce. It will not increase. Now let's say we have some load. Let's say we are dealing with a constant load and we want to start that. So what we can do, we can insert some high resistance initially, and we can cut down the resistance, say R external prime, R external double prime, triple prime, like that we have, and actual characteristic is having R external equal to 0. So what basically we do, let us say if the load is somewhere here, what we want to start at this point. So certainly our motor cannot start this with this starting torque. There is huge gap. So what we do, we insert some resistance. Still it cannot match. We insert some more resistance. Still it cannot match. So we go for the maximum point, which is higher than the load, say tau L, which is higher than the load torque. So then yes, it can start the motor for this resistance. Then the speed improves. Now the operating point, if you don't change the resistance, will be here. This is where the load torque and the electromagnetic torque are intersecting. So it will be operating at this point. Now if you cut down the resistance, what will happen? The characteristic or operating point will shift here. A better slip zone. This slip was very, very high. So it will improve. The slip value will improve and the omega m will increase. Again, if you cut down further, it will come over here. And then if you cut down further, it will come to the near wherever the rated slip is. Okay, this I am giving a little bit extreme example. Generally, we do not go with starting torque which is close to the pull-out torque or maximum torque. So we keep something like, let us say, this load value or this torque value. So still we need some resistance to operate that. And then we will have different operating point based on how we reduce the external resistance and finally come back to the actual characteristic. So the operating point will shift like this and it will reach here. Understanding my point? So whenever we have, let us say, high load torque, to start, the rotor resistance insertion method could be good. So this could be a useful method for doing that job. But again, because this is only applicable for wound rotor or slip ring motors, so then our squirrel cage induction motors cannot be helped by this method. Other method what we have seen is basically our voltage reduction method. Now voltage reduction method does not improve torque. This you will see through your analysis. It will only improve, let us say, the starting current or starting power, these things. So what will happen in this, that your maximum torque will reduce this tau max, which is basically kT by 4, and kT is basically proportional to V1 square. So whenever you reduce the supply, let's say you reduce the supply by half, your kT will become 1/4. So that's why this reduces significantly the maximum torque what you are going to see. And of course, the starting torque and everything else. So the same characteristic will be shrinked vertically. Let's say if the actual characteristic is here, something like this, then your other characteristics will be shrinked within this. So your starting torque is going very, very poor, just because your maximum torque is also reduced. Now this kind of starting is okay if we have fan load to start. Fan load means at the starting the load torque will be 0. Correct, sorry, here at the starting, which means S equal to 1, the load torque will be 0 and it will only increase with omega. So if I draw with black, the characteristic for fan load may look like something like this. It may not be significant even for few RPM of the motor operation. So if you have a load to start, which is of nature, this something shown like this, so fan load or blower or any other thing, then this voltage reduction method may be useful, because any starting torque is okay, it can improve, and slowly as you increase this voltage, the operating point will shift and it will come to its natural slip. Correct? So this kind of load is fine when you have this method. Again, so squirrel cage induction motor also can take advantage of this method. But given that the starting torque, the load torque should be very, very small, where the fan load we are talking about. It may not be non-zero, it may not be zero, it could be some non-zero value as well. So, but still it should be lower than what voltage you are providing and the corresponding starting torque. Understanding my point? Yes or no? Say something.
Yes, sir.
Yes, sir.
Clear, right?
Yes, sir.
Manvendra, is it clear to you? Manvendra, are you there?
Yes, sir. Yes, sir.
Awake? I'm not able to see you.
Yes, sir. I'm there, sir.
Where? Okay, good. At least show your face so I would know whether you are awake or sleeping. No, these feedback are very important for the teacher. If students are sleeping, then no point in teaching further. No, you can better go and take a good nap. Okay, so these methods we have seen. A little bit more elaborate, this kind of exercise you will get in your assignment and exam maybe. So be prepared. So that is how, see, whenever we are discussing that what is good, what is bad, we also need to quantify that good or bad. Now the qualitative analysis is not going to help us. So quantitatively, we should be able to say that if you are going to have this in your system, this is what you are going to see. This is the current, this is the power factor, this is the power, this is the torque. You should be able to tell very clearly. These are the numbers. If an engineer cannot tell the numbers, then it's of no use. Qualitatively, anybody can say that yes, it will be high, it will be low. That doesn't give any value to your degree or to your expertise. Your expertise comes when you can say pinpointed that yes, this is what the value is. Understanding my point? Now, obviously, in all these methods, what we are seeing that we are having, let us say, same characteristic which is either shifted along the x-axis or it is shrinked along the y-axis. So we are compromising on many things. Certainly here our starting torque is increasing, but drawing so much power, so much current is obviously not good. And in the second case, our starting torque itself is reduced. So if we have any load torque, let us say we want to start, which is here, we can never start it with the reduced voltage starting. We can never start. The maximum starting torque is here. And with the reduced voltage, you can only reduce it. You cannot increase it. So that is where we go for the other methods of starting or running the motor. So, which is where the suggestion could be that we are varying the voltage supply of the motor. We are inserting some external resistance, but we have not touched the frequency of the operation. We have not touched this point. We have done some arrangement to this, or we are inserting some resistance and all that. Now we will see what impact it will create if we try to change the frequency. Understanding my point? Now we know that the EMF what is generated across the air gap, you can say. So this is basically, you can say, some constant times of frequency and then omega and say flux. Correct? Okay, frequency, omega are same things. You can say frequency and the flux what is coming over there. Correct? Some constant is there relating all this. So 4.44 and all that, what expression, that is good enough for getting this value. Now, important thing to notice over here is that if you simply try to reduce frequency without changing the voltage at all, your flux may increase. You understand my point? So what will happen if your flux increases in the motor? the motor may saturate. And so whatever you are trying to achieve may not be possible. So somewhere we have to maintain this flux value at a constant number and for better utilization at the rated value. We will see this one more explanation of why we are keeping at rated value little bit later. So now this flux should be maintained constant. Then what options we have is that if you rearrange this, it is coming something like E1 by Fs. Which means the ratio of these two quantities must be maintained constant if you want to have a constant flux operation. Understanding my point? Now, what it suggests in terms of torque, when we maintain this value, let us say we are maintaining this as constant. What happens to the torque? Let us see first. So torque value is basically we have seen Kt S alpha by 4s square plus alpha square. What is Kt basically? 3p by 2 V1, or to be little bit accurate, it could be E1 square by omega s XLR, and then this expression whatever is there. Understanding my point? So this term, if you see, XLR is basically omega s into LLR. So I can take out another omega s from here and it can be written as 3p by 2 times of E1 by omega s whole square divided by LLR times of S alpha by 4s square plus alpha square. Which means what? That if you maintain this ratio constant by some arrangement, your torque characteristic is not changing. This is still, this constant value is maintained at Kt. Do you see this point? If you are able to maintain this factor constant E1 by omega s, then your expression or your characteristic is not disturbed. It is maintained as the natural characteristic. But what you are changing? You are changing the operating frequency, omega s or Fs. So basically what we see in effect is that if I draw the characteristics over here, and now if I draw with respect to say omega s or omega m, you can say, because that is the variable quantity. So little bit different manner I will draw than what I have been drawing so far. When you have different frequencies of operation, say this is your natural characteristic. Please mind that this is omega m, not the slip. So at 0 you have the starting torque. Now when we shift, this is the synchronous speed corresponding to say Fs1. Now we have another speed of operation. So this will be synchronous speed corresponding to that. So what will happen? Again, a new characteristic, which is very, very similar to our new, means the same characteristic only is now restricted to this new synchronous speed, Fs2. Starting torque is not changed. The maximum torque is not changed. One more will have, sorry, it should stop here. One more will be like this. Then one more will be like this. Another one will be like this. Another one will be like this. So we are getting family of curves over here. And for all such curves, we have the starting torque and maximum torque same. Now, if we can reduce this starting frequency to a very low value, effectively it will become like a straight line, something like this. It's just there, say 0.1 hertz, 0.2 hertz, it is there. It is just this straight line part. Now you can have any load. Let us say even if you have fan load, okay, black color, this, or you have a constant load of any value, anywhere, you can just adjust this operation by increasing the frequency slowly while maintaining E1 by F constant. Understanding my point? So here we have not degraded anything. We are always operating at the highest torque point. Isn't it? If our say synchronous frequency is corresponding to 5 Hertz and slip frequency is 2 Hertz. So we are very close to that. The rated slip is 2 Hertz. Then we are very close to that always. Understanding my point from the beginning. So this manner we are not disturbing our constant. And then we are able to retain the properties of the characteristics. Am I clear?
Yes, sir.
Yes, sir.
Correct? So
Yes, sir. Yes.
then this could be a very good method for any motor, let's say whether wound rotor or a squirrel cage motor. For both it is applicable. And then it doesn't need any external resistance. And because we are always operating at some good slip value, then our current, rotor current and the torque, all these things are maintained at the rated values. Power factor is always good. You can compute and do all the, because when slip is maintained as rated value, say 2%, 0.02, all the computations become good. And this 2% slip could be corresponding to any synchronous frequency. 2% of 10 Hertz or 2% of 50 Hertz. It's always 2%. What is important? Understanding my point? Now, the question comes, can we maintain this V by F ratio always? Where are the limitations? Let's say when you are saying that we are maintaining E1 by F as constant. Can we maintain this constant always? Or
Sir,
there are some restrictions? Yes,
Sir, when we are increasing frequency, then we cannot increase the voltage more than rated value.
Yes. So certainly there are some restrictions, and not just on the higher side, on the lower side of the frequency also, we do have some restrictions on this. So this discussion we will complete tomorrow. Okay. And then we will slowly move towards our requirement, the need for converter, and how to realize the power converter for this. Fine. Any questions up to this? Any questions up to this point?